Well, hi everyone. I promised I would make a video to discuss what happens with a linear system of differential equations if the coefficient matrix has complex eigenvalues. This turns out to be something that comes up fairly often, and when we have complex eigenvalues, the immediate concern is making sure that we can still come up with real valued solutions, the types of solutions that engineers would care about that don't have I in them. So one of the ways to sort of explain what to do in this situation is to just show you an example of it. It's really not that difficult, but I just want to point out a few things about it and do an example here. So let's suppose that I'm trying to, as usual, solve my linear system x prime equals ax. I'm trying to solve for the general solution for x. And let's take this matrix A right here. Okay? So it starts off, just like always, we're going to find the characteristic equation for that matrix. So that's going to be the determinant of the matrix 9 minus lambda, 29, -1, and -1 minus lambda. Okay? And if we just use our little formula for a 2 by 2 determinant, we're going to get something like this. All right? And this is going to expand out into a quadratic equation. So I have lambda squared minus 8 lambda, and then plus 20. Okay, so you can check me on that pretty easily. We're going to, as usual, set that equal to 0 here. And this does not factor nicely, so I'm going to just use the quadratic formula to get the roots, and the roots will be 8 plus or minus the square root of 64 minus 80, all divided by 2. And if we simplify that, I have 8 over 2 is 4, and this is the square root of -16, which is 4i, but I'm dividing that by 2, so I'm going to end up with 2i. So the eigenvalues are 4 plus and minus 2i. All right? Let me take off this calculation now and just put the lambdas here. 4 plus or minus 2i. Notice that there are no repeats. The lambdas do not repeat, and so this is not a defective matrix by any means. And so we should be able to write down the solution fairly simply. I don't have to use any of the other techniques for defective matrices here. This is a non-defective matrix. Okay. Now, of course, corresponding to each eigenvalue, we also have eigenvectors. So, the next thing that we might do would be to take a look at the first eigenvalue. I'm going to recommend that when you have a complex pair like this, a plus bi and a minus bi, you always want to work, just for consistency's sake, with the same sign eigenvalue. So I'm going to work with 4 plus 2i right here. All right? So as usual, I have to find the null space of the matrix that I get when I subtract the eigenvalue from the main diagonal. So when I do that, I'm going to get 5 minus 2i, 29, -1, and -5 minus 2i. All right? And as usual, these two rows of this matrix have to be multiples of each other. When we have complex numbers involved, it doesn't always look like it. It may not look like these two rows are multiples of each other, but they are. So I can cross one of them off. I usually just cross off the one that has the bigger, nastier numbers. It doesn't really matter too much. And then I'm going to use my little trick for getting an eigenvector from a single row of 2 entries, which is I'm going to reverse the order of the position of the 2 elements, and I'm going to change the sign of one of them. I'm going to change the complex number to a positive 5 plus 2i, and I'm going to leave the -1 the way it was. Okay? Now, what we're going to want to do here is actually write this with 2 parts. We're essentially going to bust out the I from the part of the vector that has I in it. So notice what I just did right here. I took the parts that don't have I, the 5 and the -1, and I made that into a single column. The I is right here. I'm kind of busting it out in the sense that we used to bust variables out. And after I do that, there's a 2 left over in the top entry, and there was no I on the bottom row anyway. So this is the vector that I would end up getting. So what I have then is I have an eigenvector, I'll call it V here, which is 5, negative 1, plus I times 2, 0. So I'm going to just kind of emphasize the results of our calculation there and give myself some room down here now. Okay? Now, normally, of course, we have another eigenvalue, which is 4 minus 2i. And we could go through, you probably remember that to get the eigenvalues and eigenvectors for a complex pair, when you go to the conjugate eigenvalue, so when I go from 4 plus I to 4 plus 2i to 4 minus 2i, all I have to do for the eigenvector, instead of actually working anything out again, I just have to conjugate the vector that I got here, which would give me this vector right down here. I don't have to go through the null space calculation again. I can just go straight to this pair. Okay, but as it turns out, for what we're doing here in Chapter 9, it's actually not necessary to write down that conjugate information at all. Because it turns out that just this one eigenvalue and eigenvector is enough to give us 2 solutions, right? It's going to give us, we need 2 solutions for this 2 by 2 linear system. And a single eigenvalue, which is complex in nature, can be used to extract 2 real solutions. Okay? So we don't really need this. Now, guys, if I was going to go back to Chapter 7, where we were writing down, you know, the diagonal matrix and the invertible matrix S, if you remember that, you know, we put the eigenvalues on the main diagonal, right? So in this case, we would have, you know, for 4 plus 2i, we'd have 5 plus 2i and negative 1, right? In this case, yeah, sure, we need to actually have the conjugate eigenvector right here, and we would build the matrix S and D as such, right? So for the purposes of diagonalization, yes, we absolutely do need to know, you know, both eigenvalues and eigenvectors as two pairs. Okay, so this is Chapter 7, back to diagonalization. We're not doing that right now. What we're trying to do now is simply solve this linear system. And it turns out that I can get away with just this information right here. I don't have to look at the conjugate eigenvalue. Okay? So let's talk about how we're going to come up with the solution. All right, so normally the x of t is just e to the lambda t times v. Okay? So in this case, of course, that would be e to the 4 plus 2i times t. And then the vector is this expanded expression here, 5, negative 1 plus I times 2 and 0. Okay? And as usual, if I want, I can FOIL this out. So I'll have e to the 4t at the beginning here. And if I multiply that by e to the 2it, that can be rewritten using the Euler formula, as we saw earlier in an earlier chapter. I can take e to the I times theta, essentially, and write it as cosine of theta plus I times sine of theta. Right, and then of course I still have the eigenvector that looks like this. Okay, so far I'm not real happy with this answer because it still has I in it, right? But what we can do next is we can go ahead and actually FOIL this out, right? We can FOIL this out. So I can take, you know, cosine of 2t, this one, times the first vector, which is 5, negative 1. Okay? So that's the first, you know, the first and the first, right? Now, it turns out that the next thing that I would want to do is put the last terms together. You see, because I times I is actually I squared, which is minus 1. So I'm going to put a minus here. Sine of 2t times 2, 0. Okay, so this is the first and last, and I'm going to group them together. And notice there's no I there at all. Okay, the first and the last has no I. Okay, now the outers and inners, okay, I'm going to give myself some room here to finish this. The outers and inners do have the I on them. So the outer term would be cosine of 2t times the vector 2, 0. And the inner term would be sine of 2t times the vector 5, negative 1. So it would look something like that. Okay? So there you go. The outer and inner part of the calculation is here. So it's FOIL, but it's better to think of it, you're not foiling it out, you're floying it out. Putting the first and last together, and then the outers and inners together. Okay? Still not quite an acceptable answer, because I've got this I still in the answer here. But as we saw back in the last chapter when we were solving problems like this, it turns out that you can go ahead and from this one complex solution, you can extract this solution by itself and this solution by itself. It would involve, to really show the math behind it, you would have to use the other eigenvalue, eigenvector pair, create another similar expression, and then do the appropriate addition and subtraction. I'm not going to show you all of that. I'm simply going to tell you that you can now go ahead and write down two real valued solutions. Okay? The first one is e to the 4t times this first part right here, cosine of 2t times 5, negative 1, minus sine of 2t times the vector 2, 0. There's your first solution. Okay? And then the second solution, well, that's going to be e to the 4t times the second part, and again, I can omit the I because I'm going to be able to get it to cancel out if I actually show or work through the details of how to get that to happen. I'm not going to do that here. I'm just simply going to write down the second solution as such. Okay? And these are the two basis solutions, so to speak, to the linear system. Obviously, it's a lot messier than what happens when you have only real eigenpairs, but this is what you have. So the general solution then would be, C1 times the first solution here. So I'll just write it out one more time just to make it very clear. Okay, so this is the first part of the answer, right? Like that. And then plus C2, e to the 4t, and now I have to put down the second part of the answer, cosine of 2t, 2, 0, plus sine of 2t, and then 5, negative 1. Okay? So this would be the final general solution. All right? Of course, somebody could come along and give you initial conditions. The initial conditions would allow you to solve for the C1 and the C2. So like if I gave you some specific numbers, like let's say I told you that x of 0 was equal to 1, 2 or something like that, right? Then if you just go through this expression and put in 0 for t, okay, of course the exponentials would go away, the signs would go away, and cosine of 0 is just 1. So you'd get a much simpler expression that would have the C1 and the C2 in them. And equating that expression to 1 and 2 as a vector, you could then solve for those constants and get a particular solution to the system. But this is the general solution. And then the initial condition would be allowed to help us find the particular solution. Okay, so that's basically how you do this. It can be a little messier if you have a larger matrix. Let me just show you one more example. Okay, and then we'll call it good on this topic. So a slightly bigger matrix would be maybe a 3 by 3 like this. So, suppose I say solve x prime equals ax, where a is the matrix. So I'll write down a matrix here again. 0, 1, 0, negative 1, 0, 0, and 0, 0, 5. Okay, so imagine that I gave you that. Okay, and I want to find the general solution to this. So, you know, as usual, we would start off with finding the characteristic equation. So I would take the determinant of the matrix that I get when I subtract lambda from the main diagonal. Okay, and this one is well set up to cofactor expand the bottom row, or the third column. So if I expand the bottom row here, I've got this 5 minus lambda already factored out, and then I just have to take the determinant of the 2 by 2 matrix right here, and that's simply lambda squared plus 1. Right, and if I set that now equal to 0, then I can figure out what my lambdas are. I'm going to have 5, and I'm going to have right here, here's the imaginary part, lambda, the square root of negative 1 basically is plus or minus I. So I have 3 lambdas. They are all distinct, so this is going to be a non-defective matrix, right? And I just have to go through and find the eigenspaces. Let me just start with the one that's already real, because that'll be fairly simple. If I take lambda equal to 5, I'm going to be looking at the null space of the matrix I get when I subtract 5 from the main diagonal. Well, it's going to look something like this. Okay? And as you can see, this is not invertible. We can cross off, in this case, the row at the bottom of all zeros. And these 2 rows right here are not multiples of each other, so you're not really going to get any free variables out of the first 2 columns. It's really the third column which is going to be free. So z will be free, but both x and y, as you can pretty quickly tell, they're going to have to both be 0. I mean, you basically have a system here. Negative 5x plus y is 0, and negative x minus 5y is 0. If you just think about solving that system, you see quickly that there's only one solution, which is the trivial one. So my vector here, after I bust out the t from the 0, 0, t, the vector that I'm going to use is 0, 0, 1. Okay? So my first solution then to this system, maybe I'm going to put it right over here in the corner so I can keep it handy. The first solution is going to be e to the 5t times 0, 0, 1. Okay, so we need to hang on to this for a little while we do the rest of the problem. Okay, I'm going to erase right here. As usual, you can always rewind me or pause the video to spend a couple minutes to look back at this. But I'm going to move on and work on the next eigenvalue. So this first solution was for the eigenvalue 5. Okay? Let's look at the eigenvalue I right now. Okay? So this is a complex number, of course, and I'm going to have to find a corresponding eigenvector. I'm going to subtract I from the main diagonal of the matrix. Alright, and it's going to look like this. Now, this time, I cannot cross off the bottom row because this pivot right here is going to be pretty solid. And in fact, if you think about the variables that go with these columns, the last equation is basically telling you that 5 minus I times z has to be 0. So z has to be 0. There's no question about that. Alright, but of the other 2 rows, okay, I have to be able to cross one of them off. I'm just going to cross off whichever one I want. I'll cross off that one. And then with the x and y variables, if I just look at this part of the matrix, I can do my same trick that I've shown you many times now, where I basically swap the negative I and the 1, and I change one of them to a minus. And I'm going to change the minus I to a positive I. And I'm going to end up with this eigenvector right here. Okay? So that is the eigenvector that corresponds to the eigenvalue lambda equals I. Okay? So when I'm trying to find, I'm going to just call this x23. Okay, this is not 23, this is 2, 3. So I have x1 right here, and I know that this eigenvalue is going to produce 2 solutions, which I'm eventually going to call x2 and x3. For the moment, they're kind of married together by this lambda equals plus or minus I, and then here's the eigenvector for lambda equals I. But let's see what happens when I write down the solution. Remember that we have e to the whatever the lambda is times t, and then times the eigenvector. Okay. Now in this case, there's no real part to the eigenvalue, so I don't have, e to the at. That part goes away, and the only thing that I'm going to be writing down here is the cosines and the sines. So there's the exponential expression written using Euler's formula in terms of sines and cosines. And then I'm also going to take this eigenvector, I'm going to take all of the real parts of it, and then I'm going to take the imaginary part and factor out the I, and end up with something like that. Okay? So now, once again, the trick at this point is simply going to be to Floy this out. Okay? I just have to do the Floy thing. Okay, so I'm going to use Floy right here to get, that this is equal to, okay, the first part would be cosine of t times 1, 0, 0. That's this times this, right? And then for the lasts, I'm going to have a minus sine of t times 0, 1, 0. Okay, so this is the first and the last. Remember, the minus is because I squared equals negative 1. All right, and then I have the I being multiplied by the outers. The outers is cosine of t times 0, 1, 0. And then plus the inner part, which is sine of t times 1, 0, 0. Okay, that's the outers and inners. So there's the Floy. Okay, so this first part right here, guys, this first part, that's the x2 of t. And this part right here, without the I in it, is the x3. Right, so my final answer, this is a slightly bigger problem, but it's not really anything different. It's the same procedure. The first term is over here on the left. The second term is going to be c2 times this vector. Well, I wanted to mention, while I'm at it here, there's no exponential here. But I did want to mention, you can multiply the cosine inside the vector and the sine inside the vector, and then you can compress this into a single vector, right? You don't have to do this, but you'll see it sometimes where, like, if I read across the top entry of the vectors here, I have a cosine of t minus 0. So that's why I'm writing cosine of t here. Along the middle, I have 0 minus the sine of t. And then on the bottom, I just have 0. Okay? And I don't have to do this, but it's something that is sometimes sort of compresses the answer a little bit, makes it easier to look at. So for this last vector, you can see that I'm going to get a sine of t right here. And in the middle, I'm going to get a cosine of t. And on the bottom, I'm going to get a 0. So this then becomes your general solution right here. Okay? And again, if some initial conditions had been given, then we would be able to actually solve for C1, C2, and C3. Okay? So that's the story with complex numbers. I'm going to leave it at that. I'm going to make a second video to address what happens kind of visually, how we can kind of like understand what this means from a visual point of view. So I really would like you to watch that one as well. But this one is pretty straightforward. You just have to get used to Floy and be careful with the complex numbers when you're doing all the calculations. Thank you guys very much for watching. Try some problems on this and let me know if I can help you or if there's any questions. All right, great. Thanks.